Good day class. We will understand three-phase power with this week's series of video lectures. In this lecture, we will try to find why we use three-phase over single-phase. We'll first describe three-phase voltages, distinguish between positive and negative sequences. Next, we will look at balanced three-phase power system, and finally, why we choose three-phase over single-phase. What do we mean by three-phase power source? If we had three plug points at home connected to this three-phase system and we viewed the waveforms in an oscilloscope, you will be seeing something like the top left waveforms here. The three waveforms will have the same voltage magnitude but will be 120 degrees apart with respect to each other. What will we get if we add these three-phase voltages? This is the VA waveform, this one VB and this one VC. This is the same as the phasor representation what we have here. The summation VA plus VB plus VC, clearly we can see that it is 0. This is what is called as a balanced three-phase supply. The voltage sources defined can be either positive sequence or negative sequence. In the previous slide, we labeled the voltages like this, with VBN lagging VAN by 120 degrees and VCN leading VAN by 120 degrees. What if I change the notations to this sequence? I put VA, then VC and then VB. This is still a three-phase balanced supply. We can label these sequences either positive or negative sequences. The positive sequence is called the ABC sequence while the negative sequence is called the ACB sequence. If we assume the RMS values of the waveforms to be 1 unit, we can represent the waveforms as given in the figures here. The positive and negative sequences depend only on how we label the wires. The actual waveform does not change but just the notation changes. Next, let us look at how a three-phase circuit is different from three single-phase circuit. Three single-phase circuits is three single-phase voltage sources supplying three loads independently. In three single-phase circuits, we have three neutral conductors here. A three-phase circuit can be obtained by connecting the three neutral conductors of the three single-phase circuits together. This can be redrawn like this with a common neutral terminal. This reduces the number of conductors from 6 to 4 or reduces the number of conductors by 2, or we effectively have a savings of 33.33%. This reduces the cost of laying the conductors and reduces the power losses in the overall system. If the load impedances are equal in a three-phase circuit, we call it a balanced three-phase circuit. A balanced three-phase circuit has balanced voltage sources and identical impedances. If we say that the voltage sources are one angle 0, one angle 120 degrees and one at an angle of minus 120 degrees, we will have a balanced voltage source. Now, the current through each impedance from each of the sources can be written as IA is equal to VA by Z, IB is equal to VB by Z and IC is equal to VC by Z. Applying KCL at the common node P, IA plus IB plus IC is equal to IN, or we can write it as VA by Z plus VB by Z plus VC by Z, which is 1 by Z times VA plus VB plus VC. Now, VA plus VB plus VC is equal to 0 as they are a balanced three-phase voltage source. We get IA plus IB plus IC is equal to 0, which is equal to IN. Thus, the current in the neutral line is 0, or there is no need to connect the neutral line in a balanced three-phase circuit. This reduces the number of conductors from 6 to now 3. Let us summarize the advantages of the three-phase system. When compared to three single-phase circuits, three-phase circuits have better use of equipment and material, as we end up using only three-phase conductors instead of 6. This also reduces power losses in phase conductors. This also implies that there is a reduction in capital and operating costs of transmission and distribution. A very important advantage of the three-phase system is that we can calculate voltage and current from only one phase and refer to the other phases quite easily. Let us look at an example to understand the last advantage. Consider the following three-phase system shown below. Find the current IZ when the impedance is equal to 100 ohms. We see that the voltage sources are balanced ABC positive sequence and the impedances are identical. Hence, we can say that it is a balanced three-phase system. Thus, the neutral current will be 0, or I can write it as IA plus IB plus IC is equal to 0. We can find our IA as VA divided by Z, or 100 at an angle of 0 divided by 100, which gives us a value of 1 at an angle of 0 degrees amperes. We can similarly calculate the other currents, or we can use a phase shift of 120 degrees to get IB as 1 angle minus 120 degrees and IC as 1 angle 120 degrees amperes. In this lecture, we understood what a three-phase system is, differentiate between positive and negative sequences, how a three-phase differs from a single-phase system, and the advantages of the three-phase system. Thank you.